This lecture, I'm going to touch on the last piece of the kNN puzzle, which is how to avoid overfitting with kNN, or on the other hand, how to overfit. So we've talked about other types of models or other families of models, the main ones being linear discriminant function models and tree-based models. And so the linear discriminant models, the decision boundary is a line. And if you think about it in terms of flexibility or ability to really fit to small variations in the underlying data, linear models are the least flexible. They have the most structure. They make the most assumptions about the relationship between the x's and the y. Decision trees still make some assumptions. They assume that the relationship between the x's and the y can be captured in this set of axis parallel rectangles, or these carving the instance space up into smaller rectangles. But they're more flexible than a line. They're not just a line. They can be a little bit more flexible based on what the data is. Nearest neighbors models, especially one nearest neighbors, are extremely flexible, and so small changes in the underlying data can result in big changes in the predicted values of the y. And so we can see in this one nearest neighbors decision boundary that I've shown on the slide, it's a lot. Since we've talked more about overfitting in the class, you can see that it's a lot more likely to overfit with k-nearest neighbors than with other types of models that we've talked about. And so now that we've established that nearest neighbors methods can overfit a lot more easily, we can control the extent of overfitting by selecting an appropriate k. And so on the left, I have one nearest neighbor classifier, and we can see that the boundary is very complicated, right? A one nearest neighbor model is a more complex model. The predictions that it makes are more, there's a lot more variance in those predictions. The 15 nearest neighbor classifier, so as we increase k, the decision boundary gets smoother and simpler, and we end up with lower variance, higher bias classifications. And so to avoid overfitting, we usually select a higher k. Now, how do we know it's the right level of overfitting or not? And the real answer, of course, as everything else in this class, is we have to see the validation performance. And so let's say we have, this is an analytics interview question that has actually been given to former members of this class. So the question is, when running a k-nearest neighbors analysis for 100 data points, you're trying to choose among three different models: k equals 1, k equals 10, and k equals 100. Which one is most likely to be correct? So let's think about what happens when k equals 1. K equals 1 means we only use the y value of the one nearest neighbor. We're not averaging over any multiple set of neighbors. We just have the one nearest neighbor. So we end up with this very complicated decision boundary, and it's also a very high variance classifier. If we changed our underlying data a little bit, our predictions could change quite a bit. When k equals 100, we end up with the average prediction for the entire training set, right? We use every neighbor in our predictions. So we're probably underfitting with k equals 100. So k equals 10 is probably the best k from these three. But really, to choose k, just like we've done with other methods at this point, we have to treat k like a hyperparameter that we tune using performance in a validation set. And so we'll compute the misclassification rate, or conversely the accuracy in a validation set for a range of values for k, and we choose the best value based on the performance in the validation sample. And those are all of the important technical details that go into the k-nearest neighbors algorithm.